Very good morning. Today we are going to discuss about kinematic analysis of simple mechanisms in the subject of kinematics of machinery. Kinematic analysis simply is called as analysis of the mechanism, how much the displacement, what is the velocity, what is the acceleration. So we have to going to find what's the velocity, acceleration of the linkages. So distance and displacement. Distance means the length of the actual path traveled by the body. It is scalar quantity. If displacement means the short distance from the initial position to the final position of the body is called displacement of the body. It is a vector quantity. In which direction it is traveled in the distance is called displacement. So it is a vector quantity. Velocity means rate of change of displacement of a body in a particular direction from one place to another one place with respect to time taken. If acceleration means change of velocity with respect to time taken, so it's called acceleration. Then change of acceleration with respect to time taken is called as, we simply called jerk. Next we are going to discuss about the instantaneous center of rotation. What is instantaneous center of rotation means at this instant for a floating linkage, which one is the center for the rotation of the motion. The combined motion of rotation and translation of the linkage is happening in a floating linkage. It may be assumed purely rotation about some center. So that center is known as instantaneous center or virtual center of rotation. In many cases, a body has simultaneously a motion of rotation as well as translation. For example, the wheel of a car moving on road surface having rotary as well as translation motion. Like that. So consider a rigid link of AB which moves from its initial position of AB to final position of A1 to B, shown in figure. AB has reached to A1 B dash position through translatory motion, and from A1 B dash to A1 B1 through rotary motion. So it is a combination of translation and also rotary motion. So the figure B shows the linkage AB has. First it move in the motion of rotary from AB to AB dash about A. Then the motion of translation from AB dash to A1 B1. Thus A1 B1, which is the final position of AB, is combination effort of translation and rotary motions. This combined motion of rotation and translation of the linkages AB has may be assumed to a pure rotation motion about some center is known as I, instantaneous center of rotation. Velocity of a point on a link by instantaneous center method. Consider a link of AB which having the points A and B are end, C as the midpoint. Let us the velocity of the point A is VA and velocity of the point B we called VB. From the point A we know the magnitude and velocity, as well as from the point B we know the velocity only. By drawing perpendicular the line of A and B, we can get instantaneous for instantaneous centers. So because of debating about this instantaneous center, let omega be the angular velocity of the link AB in the plane of rotation. Velocity of the point A can be write as VA. That will be equal to angular velocity of the link into the distance from the instantaneous center to the point A. We get the velocity of A. From this equation we can get the angular velocity of the link omega by dividing the velocity of the point A, then divided by the distance from the instantaneous center to the point A. Similar as for the point B also, velocity of the B will be equal to angular velocity of the link, then multiplied by the distance of instantaneous center to the point B distance. So from this equation also we can get the angular velocity of omega. So the relationship between the VB divided by IB is equal to VA divided by IA. From this equation we can get the values of unknown value. So magnitude of velocity VC for the midpoint we can find by using same as the similarity. VC will be equal to IC into omega C. So the VC is equal to the direction of VC will be the perpendicular to the IC line. So the relationship between these three things may be VA divided by I and I2A equal to VB divided by I2B equal to VC divided by I2C, that will be equal to omega. From this equation it can be stated that the magnitude of the velocities of the points on the link is directly proportional to the distance from the instantaneous center. The direction of the velocity is perpendicular to the line of join them with the instantaneous centers. Number of instantaneous center, it may be noted that there will be one instantaneous center for two links having relative motion between them. Therefore the number of instantaneous center in a mechanism having n links will be equal to the possible pairs of two links taken at a point. Mathematically the number of instantaneous center n in the mechanism is given by capital N is equal to small n into small n minus 1 divided by 2. In this equation small n indicates the number of links. Types of instantaneous center. The instantaneous center can be classified into three categories. One is the fixed instantaneous center, then next one is the permanent instantaneous center, then another one is the neither fixed nor permanent instantaneous center. Angular velocity ratio theorem. The theorem, the angular velocity ratio theorem states that the angular velocity ratio of two links relative to the third link is inversely proportional to the distance of the common instantaneous center from the respective center of the rotation. Consider a 4-bar mechanism and locate all the instantaneous centers shown in figure. When the link AB rotates with an angular velocity of omega 2 in clockwise direction, then the line velocity of the link 2 is given by velocity BA, that will be equal to omega 2 into AB. So from that we can find the velocity of B with respect to A. So the V2, that will be equal to omega 2 into the distance from the I12 to I13. So by using this distance we can able to find the velocity of 2. Significance of coincidence of points. When the coincident point exists in a mechanism, to find the total acceleration at a point we have to calculate one more acceleration component which is known as Coriolis component of motion. So Coriolis component of motion means a sliding link slide over a rotating link, means it is called as what, that Coriolis component of motion. So it consists of total acceleration, that means radial and tangential acceleration, along with them there will be an Coriolis acceleration. So by using this we have to find a total acceleration at a coincident point about another point in a link is the vector sum of the radial acceleration, tangential acceleration and the Coriolis acceleration. So Coriolis acceleration component will be considered. So acceleration of AB will be equal to acceleration radial of AB plus acceleration tangential of AB plus acceleration of Coriolis component of AB. Using that we can find the acceleration of the link AB. Thank you. Sir, meedi langi sir.